Good afternoon. So finally now we have come to the point where we can start looking at turbulent transport. So if we recap from the beginning of the course, right, I pointed out that we have three goals. The first was to understand the connection between the continuum equations for diffusion and the microscopic description for individual Brownian trajectories, right? Not just in Brownian motion, but in general. So that took us to consider stochastic processes, Markov processes, eventually the Foucault-Planck equation. Right? Then the second point was to look at what is the mathematics governing these Langevin type stochastic differential equations, right? So the mathematics of SDs. And that is what we covered in the second part of the course, seeing the connection between that and the Foucault-Planck equation, but also what is the mathematical status of SDs from the perspective of stochastic calculus, where we realized there is different ways of defining the stochastic integral. Ultimately, Ito and Stratonovich are two useful ways of looking at it, right, for the reasons we now know. But as we've just seen, that when one thinks of SDE as a white noise limit, then you need not always get Stratonovich, right? You can even have some other definition where you evaluate the coefficient of the noise at some other point. So that's what we did in the last class. And so finally, we now have all the mathematical machinery to attempt the third part, right, which is how can we model turbulence, rather the effects of turbulence on transport, whether of heat, mass, particles. Right? Can we replace the turbulent velocity field by some random field, right, and account for its effect in a similar way to how we account for the effect of molecular fluctuations at the macro scale. Right? So if you're looking at some macro scale concentration field, we account for molecular fluctuations with a diffusion term. Right? Similarly, can we account for the effect of turbulent fluctuations, right, again in some kind of averaged way? Of course, engineers do this all the time through eddy diffusion, but is there a mathematical basis for this eddy diffusion? Right? And can we get a deeper insight into what exactly are the assumptions under which this eddy diffusion type way of accounting for turbulence, right, would be valid? And to see it from this perspective of stochastic modeling. That is the goal now, not only for eddy diffusion, but also to look at transport of small particles in the same spirit as we did the Brownian motion. Okay, so that's what we'll do now towards the end of the course. Okay. So today's lecture, I want to give a brief introduction to turbulence, the essential ideas of what's called Kolmogorov phenomenology, focusing on the things that we need to be able to do this stochastic modeling. Okay, so if we have to replace a turbulent velocity field by some random field, we would like to know how we should set up this random field. Right? For example, if we are in a periodic cube, just for simplicity, right, then we know that a Fourier basis would represent any velocity field. But how many Fourier modes should I take? Okay, the amplitude of these modes should be random because I want it to fluctuate. But should there be some relation between the strength of these amplitudes as a function of the Fourier wave number? That means different scales in the velocity field, do they have some particular relation? Right? So these are the questions that we need to have answers to before we cook up some synthetic random field and then look at the corresponding SD. So that's what I'm going to focus on today. Right? What do we know from the theory of phenomenology of turbulence that will give us the input information we need to do our stochastic modeling? Okay, I'm going to do it quickly. So to support this lecture, especially if you're interested in understanding the details and more generally things about turbulence, here are some resources that I will show you now and leave you to explore it later on. Okay, so there are a couple of good YouTube lectures which kind of supplement what I'm going to talk about today, with movies showing you experimental results, etc., okay, which I will not do now. So one is by Jeremy Beck. The title of the YouTube video is Statistical Physics of Turbulence. Particularly lecture 1 will be helpful, but you can also look at, I think there are 3 lectures. And it's on the YouTube channel of the International Center for Theoretical Sciences, ICTS. The same channel has a series of lectures by Shamridhi Shankar Ray on Introduction to Fluid Dynamics and Turbulence. I think there are 5 lectures. So again, you can go through that. This will give you similar to what I'm doing today, but in more detail with nice movies and also experimental data to show evidence for some of the ideas I'm going to talk about. And then for a detailed systematic textbook, which is also very good as an introduction, for a first start is Davidson's book on turbulence, subtitled Introduction for Scientists and Engineers, I think, by Oxford University Press. Get the second edition, okay, which has some updates on DNS and so on. That's in 2015. Okay, this is easily available. I think it's in the library as well. Okay, so those are some resources to look at later, but yeah, we'll now in this class focus on the essentials. Okay. So let's start with, of course, the origin of turbulence theory is the Navier-Stokes equations, right? Or the way we would think about turbulence is they are solutions in the end to Navier-Stokes, but dynamical multi-scale solutions. Okay, so I'm writing down the equations in scale form, right? I'm sure you know how to do this. Right? If you write the dimensional equation, scale it with length, velocity scales, divide by pressures, divide by density rather. So this is pressure normalized by the density. We're of course considering an incompressible fluid, so the density is a constant. And then you will get the Reynolds number sitting here, right? And this equation will be fully dimensionless. Right? U is a vector. So this is the normalized pressure as a scalar. Fine. So this is the well-known Navier-Stokes. Okay. Of course, you have the continuity equation. Okay. So this is the closed system of equations which we can solve given boundary conditions, etc. Now, a particularly simple problem is that of homogeneous isotropic turbulence, okay, which is the situation when walls have no effect on the flow. Now, experimentally, one can think of it like if you have turbulence in this room generated by some fans. Then somewhere in the middle of the room, far from the walls, you would expect that whatever is going on is not going to be strongly influenced by the wall. There will be no directionality to this flow. So at any instant you see a strong gust in one direction, some other time it could equally happen in the other direction. Right? So it's isotropic and homogeneous because the properties of the turbulence are not changing in space. Of course, in some limits. As I approach the wall, the behavior will be different from the center. So experimentally, one would realize this by generating turbulence and then looking at it far from walls. Okay, it's approximately homogeneous isotropic. The reason we are interested in it is because mathematically it's a clean problem to look at which focuses on the essentials of turbulence per se without getting influenced by the wall or some other effects. So in a computational way, one can realize it easily by looking at the Navier-Stokes and solving these equations, for example, in a periodic cube. So there are no walls. Okay, and so the periodicity imposes some restriction, but if you do statistics properly, you can deal with that as well. Okay. And so what one would normally do is you need some way to drive the flow, right? If I just look at it like this, U equal to 0 is of course a solution. So unless I'm driving the flow by either having some moving boundaries, like if I have a fan, right, or a moving wall, or unless I apply a body force, right? So when you apply a pressure gradient, it's like applying a body force. So what I'll do here is add an extra force. So computationally, what is done is this is some three-dimensional force, right? You give some forcing field, you push the fluid somewhere, you pull it somewhere, right? And in that way, you drive some flow. Typically, this force is a large-scale force, right? So you can think it's trying to mimic, let's say, a big fan in the room. And the whole interesting thing about turbulence is when you force the fluid at some large scale. So example, this body force could be something like sin x on a 0 to 2 pi box. That means I push in half the box, I pull in the other half. Right? This is now a computational exercise. Right? You just apply a body force, pushing and pulling. You can realize this through, for example, in experiments, people will use magnetic fields or speakers, right, to generate pressure variations, which will again be like some body force. So anyway, you can apply these body force. The point is at large scales. So if I zoom in to a small distance, there are no real force variations. Right? The fluid could just go in a straight line. You're not stirring it. So you're stirring the fluid at large scales. But what's interesting about turbulence is without you imposing it, there will be flows, small scale eddies, vortices, variations at much smaller scales. Right? So if the flow is laminar and I stir the fluid, like you imagine taking tea in a cup and you stir it with a spoon slowly, then the circulation will happen on the scale of that spoon. You will not get small vortices. But if you stir it vigorously using the same spoon, but now automatically you will get small structures. Right? So that is when we say it's transition to turbulence. So the important thing is this F is going to be some large scale forcing. I'll just write that there. Okay, so I take the Navier-Stokes as is, and what I'm inputting is some large-scale forcing. Okay. Now, if the flow is laminar, I will get some solution, of course, because it's being driven. But a laminar solution need not be steady. Okay, but the idea is we say it's well ordered and so on because it basically mirrors this large-scale forcing. Right? So if I drive the flow like this, with some forcing in this way, the fluid also will do some motion, like two big vortices, for example. I won't see a whole bunch of complicated things going on. But when it transitions to turbulence, you'll get all these different kinds of vortices across all scales, and it becomes so complex that, in fact, you lose the signature of the forcing. Just by looking at the flow, I will not be able to tell how exactly I put in the body force. And that complexity, in fact, comes to our rescue. This is part of, related to what I showed in the first lecture, the point that Poincaré made, right? That what allows us to treat systems either is their extreme simplicity or their extreme complexity. Right? So here the complexity of the Navier-Stokes, which can take some particular forcing and generate all kinds of small scales, right, helps me because it means this large scale forcing, the details are not important. So what I mean is whether I force it this way with two smooth vortices, or maybe I force it like this, right? If it is laminar, the two flows will look very different. But when it is strongly turbulent enough, they will have the same statistics. They'll be indistinguishable. The only thing that will matter is the amount of energy I'm pumping in. Okay, so in what I'm going to talk about today, this is true, of course, in homogeneous isotropic turbulence, right? Where to a significant extent, we've seen in experiments that you get this universal turbulence state, right, which doesn't care about the details of how you forced it. Right? What matters is only how much energy you pumped in. We'll come to that again in a second. Okay, so what I'm going to talk about today, you will not see any reference to walls, boundary layers, etc. Right? That is specific only to this homogeneous isotropic, relatively simple case where in the end you get some turbulent state that forgets the forcing, forgets the large scales. This does not happen in many wall-bounded flows. So for example, the turbulence you get by shooting a jet into a bath of liquid will be very different from the turbulence you get in a pipe. Okay, these statistics won't be the same. So there are many, many complications in the field of turbulence. But for the purpose of this course, we are going to restrict ourselves only to homogeneous isotropic, just because the essential idea has become clear. How to extend this to other flows is of course interesting, right? Which this course provides a basis to do those things. Okay, so let's get back to our simple situation, right? So here walls are not important. The only thing is I'm putting in this large scale force. Okay. Now, how does one see the key point about this generation of many scales, right? One way is to look at the energy equation by averaging over the box. Okay. So I get the energy equation for the box. Right? So I'm solving this equation in some cube, let's say of some length. And now I'm going to calculate the total energy budget in the entire fluid. Okay, so what I will do, already the equations have been written per unit mass because I divided by density. Right? So I just average out the volume, I'll get total kinetic energy per unit mass of fluid. So to do this, I take the dot product, right, with U and average over the box. So I multiply the equation with U and take the average. Now when you do this term, you will be able to rewrite it as a flux. Means I'll be able to take it out and say divergence of U into U into U. Okay, something like this. It also makes physical sense because this is just, the inertial term is convecting momentum. Right? So the energy that you supply in, this will just move around in space. When I average out the whole box, it will make no contribution. So mathematically, I can rewrite this and the pressure term and part of this stress term all as divergences, which when I integrate out over the box will cancel, right? Provided you have boundaries which either the velocity goes to 0 or in this case I'm doing periodic boundaries, so they'll cancel out. So what I will get in the end is going to be, and this is there in any standard book, right, when you do the energy budget. We'll get the mean kinetic energy in the box. The only term that will survive here, this will go off, okay, because again, pressure, what is pressure doing is just pushing the fluid around. It's distributing energy within the box. Okay, it's not going to, unless from the wall you are imposing differences in pressure. But here we are doing periodic boundaries. Okay, so in a pipe, for example, you will have high pressure here, low pressure here. So when I integrate across the pipe, there will be a pressure difference, which when you take dot product with U will give you power. Right? That doesn't happen here because we are imposing no macroscopic pressure difference. So this guy goes off. Here I will get this dissipation term, which will be familiar to you. Right? Okay, this is the viscous dissipation. Remember, 1 by RE means there is viscosity on top. Okay.
So what is that?
2 kinetic energy per unit mass. Okay, this is the viscous dissipation. And then, of course, I have the forcing dotted with the velocity, okay, averaged. Okay, so this is the equation now. It's an energy budget, right? What it tells me is the change of kinetic energy is really a balance between the input of energy here and the dissipation, right? So this is input because of my forcing, and this is happening at large scales, and this is dissipation. Okay. Now, when the flow starts up, of course, the input will be much larger than the dissipation, so kinetic energy will grow. You can imagine I'm starting to stir the fluid. And at some point, it saturates. When I say saturate, it doesn't mean you reach steady state, right? That will happen if you actually have a steady, that will be a laminar solution. Turbulence is always fluctuating. So this is always fluctuating. Okay. But when I say stationarity, I mean its statistical properties are not changing anymore. Right? There are fluctuations, but if you calculate the mean, variance, all these things are the same. So one way of thinking about this is you look at averages over time. That's what we would do in an experiment. But theoretically, we would say, okay, I use ergodicity and I say that I'll do an ensemble average in addition to the box average. So you can imagine I'm doing many such experiments, same box, I run the experiment and then I do it again and again and again, and I average out that at every time. Then if this is in addition to being a box average, also an ensemble average, right? So I do it over the box and over the ensemble. Right? Then at what's called a stationary state, that means the statistics are no longer changing in time, right? This will go off, right? So at the stationary state, there is no change of kinetic energy, right? In dissipation and the input will balance, okay? So this is the mean dissipation, right, is equal to the mean input. Because that's not surprising, right? This is just pretty obvious, right, that I'm putting in energy into the fluid, and for me to get some kind of stationary statistics, that energy has to be dissipated. Okay, and the dissipation in a classic Newtonian fluid will only be viscous. There's nothing special about it. Now, what the first interesting thing, this is pretty obvious, right? The first subtle interesting thing is when one thinks about the fact that the dissipation term is multiplied by the inverse Reynolds number. Okay, so of course, Reynolds number has different parameters in it, right? The size of the system, so on, right? And you can manipulate Reynolds number by changing those things. But here we'll focus on, which is easy to think about, is the kinematic viscosity, right? Mu by rho. So Reynolds number is length. If you want, this is large scale Reynolds number would be some large scale at which I'm putting in the forcing, right? Capital L. The velocity at that scale, Lu, by kinematic viscosity, mu. Okay. So now, as this Reynolds number gets bigger and bigger, right, this is when we know that flow will become turbulent. Right? You see what happens to dissipation. So normally it looks like this dissipation term will start to shrink, right? If I increase my Reynolds number, and now if I think, as mathematicians will, let me just take Re to infinity. Right? But physically also you can think about this because you can go beyond the lab scale to turbulence in the atmosphere. Right? Then you can go to turbulence at planetary scales. Right? There is also astrophysical turbulence that happens at galactic scales. I mean, you can keep going. So Re can really be very, very large. Right? So as you go to those scales, you'd think the dissipation would get knocked off. Right? And if that happens, how will I ever attain stationarity? Right? Then it doesn't make any sense to have Right? At the same time, the kinetic energy cannot keep on growing. Right? So for the dissipation to balance the input as RE increases, right, what has to happen? So there are two terms here, right? There is this 1 by RE term, and then there is this actual mathematical quantity. Now, normally when we scale, if you scale properly, you will use some length velocity scale such that the magnitude of this term is 1. Only then 1 by RE controls the magnitude. Okay. But that is an assumption that whatever large scale, so typically RE would be defined, okay, where L is large forcing scale of the force F, okay, and U is the corresponding velocity at the large scale. So you can think about it in some experiment. I have some big fan in the room. The size of the fan blade is capital L, and the velocity of the tip of that thing is capital U, okay. But it doesn't really matter. You choose some large length scale and velocity scale and property of the fluid, you will get RE. Now, as I make the viscosity of the fluid smaller and smaller, RE will grow. Okay, that's what I'm saying, right? So, what happens as RE goes to infinity? Right? Nominally, it looks like this dissipation will become smaller and smaller, but that's assuming that this velocity gradient's magnitude is really decided by U by L, the large scales. But what this fact that this balance must still hold if we have to get a stationary state at increasing Reynolds number tells me that this assumption of scaling is wrong, right? This grad U double dot grad U is not given by capital U by L. Because if this 1 by RE gets smaller and smaller, the only way to maintain the balance is this velocity gradient has to become large, it must go greater than 1. That just means that my scaling assumption was wrong. The magnitude of grad U is not capital U by capital L, it's something much larger. Now, how will that become larger? It will become larger if I can somehow generate smaller scales so that the U by L grows, right? So as L gets smaller and smaller, and as long as U doesn't grow as small, it will grow, right? So what happens is somehow the Navier-Stokes, through a sequence of fluid mechanical instabilities, right, which of course are have been studied for a long time, continue to be studied, right, the mechanisms. But if we set aside the mechanism, somehow the Navier-Stokes, through this nonlinearity, okay, which is very important, it got lost in the energy budget. But it's actually crucial. If it was not there, the equation would be linear, no turbulence. Right? So this thing is this nonlinear term, okay, which is responsible for all the nonlinearity, therefore all the instabilities and so on. Right? This nonlinear inertial term is what's responsible for generating stronger and stronger gradients in order to make this budget work. And all that means when you say generating larger gradients, it means you're creating smaller and smaller scales. Okay, so where I had this large scale forcing, right, with some large scale velocity U, that the gradient there is too weak to give me enough dissipation, right, once the RE is made large enough. So the only way I can keep dissipating is from this large scale, I need to somehow, that big vortex, if you like, has to break up, some instability has to happen, and I have to generate smaller vortices. Right? Those smaller vortices must have enough velocity, small u, so that when you divide by their small length, you get a larger gradient. Right? If that does not happen, then you will not be able to satisfy this. Okay, so you can see physically that what for turbulence to sustain or for this energy budget to work, somehow the fluid has to generate smaller and smaller scales which have strong gradients. Right? The gradients have to keep growing as the Reynolds number is increased. Right? So as RE grows up, right, the gradients become stronger, become ever stronger. Okay? So that the dissipation keeps matching this, which is fixed. Right? So as I'm increasing RE, I'm not changing the input of energy. Right? So that's why I said it's good to think about increasing RE by decreasing the viscosity. So you're doing experiments with different fluids, right? You start with honey, you go to water, you go to air, and etc. Right? So if you do that, F dot U will be same. I'm applying the same forcing force. It's producing the same velocity at the large scale. Right? Anyway, the viscosity will not affect the large scale motion once the RE becomes small. And now as I keep making RE bigger and bigger and bigger, right, this is fixed. So somehow to have this product be the same, grad u double dot grad u has to grow up. So already energetically you can see that for a stationary state to exist, right, at very, very large Reynolds number, I must somehow have to generate small scales and large gradients. And if those large gradients are not being provided directly by the forcing, then they are happening automatically through the fluid mechanics, right, or spontaneously. Okay, this is what we mean when we say turbulence is an emergent phenomenon, right? I am not putting in the information. Spontaneously is generating small scales. And what will become interesting, as you can see, is as you increase the Reynolds number, those scales have to become smaller and smaller, right? Because the gradients have to grow larger and larger. So you will have this situation where you're forcing the fluid at very large scales, but at high enough RE, you're producing extremely small scales. And now you can imagine that those small scale motions will not care about the large scales because it's such a big scale separation. So this is the basis to expect that at small scales, the forcing will not matter. What matters is only this input. Okay, anyway, so this is the crucial point, right? That as RE increases, the grad u must become stronger, and therefore, right, small and energetic. We'll be more precise as we go along. So when I say energetic, it's because the gradient at the small scale is some small u by L. Okay, so I'm going to use any scaling arguments here. Right? So capital U is the typical magnitude of the large scale velocity at scale capital L. Now imagine I produce some smaller scale, small l, which has velocity small u. U by L will be the strength of that gradient. Right? For this to be large compared to capital U by L, it's not enough that u decrease, right? L decrease. L should be small compared to capital L, but u also should not be as small, otherwise it will remain a constant. Right? So imagine u decreases along with L, then it will stay a constant. So if I decrease the length scale at some rate, u must not decrease as fast, right? So that means the energy has to be relatively strong. That's why I'm saying energetic scales. Okay? Otherwise, if the velocity scale decreases proportional to the length, you will just get a constant gradient. That's what will happen. That's the definition of having a constant gradient. Right? If I have a flow in space, the gradient is the same everywhere, then that just means u is proportional to L. So for the gradients to increase, I need the small scales to have relatively stronger velocity than I would expect if I had just a nice constant gradient. Okay, so that's where the complexity will come from, or the seeming complex nature of the flow field. Okay. So small energetic scales have to be generated spontaneously in the flow, right? So that in the end I have this balance, right, of the input of energy and the dissipation. Now this idea is actually, you've seen it before, right? You would have seen similar ideas. The same idea underlies the concept of boundary layer. Okay. So if you have flow in a pipe, again you can write down a similar relationship. Instead of dissipation, you will be calling it drag, right? So the total drag, which gives you the pressure drop in the pipe, right, will have some relation. And now as you make the viscosity smaller and smaller, what happens? The drag in the pipe doesn't go to zero. So you remember Moody's friction factor, right? Right, the pressure drop in a pipe, right, which is of course supposed to balance the dissipation of energy because of the drag on the wall of the pipe, right? So that pressure loss, right, the loss term, is Moody's friction factor, depending on how you define it, right? Rho u square by L. Correct? No, rho u square L by D or something like this. Right, so these are dimensional things that come in, and then the friction factor is there. The friction factor is supposed to be a function of Reynolds number. Right, and when you plot the friction factor versus RE, so basically if you keep everything fixed and I just change the viscosity of the fluid, only the friction factor will change because the Reynolds number will change. Right, so the friction factor will set the pressure loss, that means the kinetic energy dissipation. That's exactly this stuff, the analog of that. And what do we get in the friction factor plot, right? It decreases and then it flattens out. So we are used to thinking about this as increasing the velocity magnitude usually, right? So when you think of RE as I'm making the flow rate larger and larger, then we will say, okay, it means the pressure drop is increasing with flow rate. Why? Because you have U square there, right? So as long as this decrease is linear compared to U square, so the pressure will increase with U. And when it flattens out, we'll say the pressure drop becomes more because it grows by U square. That's how we think of it normally. But if you think about Moody's chart in terms of changing the viscosity of the fluid, as we were doing here, right? So I increase RE by taking fluids of lower and lower viscosity. Now U square is fixed, right? So directly the friction factor controls the pressure. So now what you see is as I make the fluid, right? So RE is increasing here, and the kinematic viscosity is, increasing, and nu is decreasing. Right? So as the kinematic viscosity decreases, the Reynolds number increases. So initially, as the viscosity decreases, I do get less pressure loss. Makes sense, right? So if I replace honey by water, by air, the amount of dissipation to the amount of pressure loss I will have if I pump a fluid of lower viscosity should be less. This is what happens in the laminar regime, where this behaves like 1 by RE. Then you have the transition where it slows down. So it's not decreasing as fast as it was earlier. And then it becomes flat. Okay, so what does this mean? This is very deep, right? Which maybe you didn't realize earlier. That the fact that it's flat means the dissipation is not reducing anymore. So even though I'm taking a fluid I'm replacing my experiment with fluids of lower and lower viscosity, right, which dissipate less and less, I'm not actually getting any more reduction in the dissipation. It's staying the same. Okay. And that's exactly what I'm saying is here. Right? That even though I increase the Reynolds number, I'm able to maintain a balance. I'm keeping the dissipation the same, right? And that's happening because I'm producing these large gradients. Same thing happens in this regime, right? I develop these boundary layers near the wall. I start developing strong internal gradients in the fluid, right? So then as I replace the fluid with an even lower viscosity fluid, the flow field is changing and becoming more and more turbulent with stronger and stronger gradients. So it's dissipating the same energy. Right? So if you like, this is a bottleneck on trying to achieve, trying to reduce the pressure loss. Right? Beyond a point, you cannot do it. Right? Because the turbulence becomes stronger. If I increase the RE by decreasing the viscosity, the turbulence just becomes stronger to compensate. And by that I mean you get stronger gradients. Okay, so we've seen this before in Moody's friction fact chart. Also you see it, that's the basic idea in boundary layers, right? That you cannot, by making RE go to infinity, you will not get the limit of a perfect fluid, because then it would mean you could send fluid through a pipe without any pressure loss, right? Or that there would be no drag on a sphere, D'Alembert's paradox and so on. So we know that the resolution is that there is a boundary layer. But that's just like saying there's a layer near the solid where there are very large gradients. Okay? Now I don't have a solid wall. That doesn't mean there cannot be boundary layers. There are internal layers. So just like near a wall, you will have a region with large gradient where you can dissipate and viscosity becomes important. Even if there are no walls, right, because of fluid mechanical instabilities and turbulence mechanisms, you will generate internal layers where there are large gradients, where viscosity will be important, and where you can dissipate this energy. Okay, so all these ideas are connected. This generation of small scales, etc., are all connected to the fact that this is a singular perturbation. Okay. Let me. Right, so I'll say okay, so mathematically that is what we mean, right? That as we take RE to infinity, I cannot get the solution by dropping off this term. Right? This term always remains because these internal gradients keep changing. So that is what's called a singular perturbation. So the flow you will get by taking the limit of RE going to infinity is not the same as if you start the equations where RE is infinity. That means the equations without the dissipation. Right? Those will be Euler's equations. They will never dissipate. Right? So you never get that solution by taking RE to infinity because you keep generating these stronger and stronger gradients. There are all kinds of mathematical questions, including this millennial prize problem and the existence of solutions to Navier-Stokes connected to this issue. but some of that is discussed in Jeremy's lectures. Okay, so the basic message we have now from this discussion is that fine, when I achieve stationarity, and we are going to be looking at turbulence in this statistically stationary state, a stochastic model for turbulence will be some Markov process that is stationary. Okay, so in that state, we know that the dissipation must balance the input, and by our specification, the input will happen at large scales. Right? And now we've just argued that if RE is large enough, then the dissipation will happen at small scales. Okay, so that is the main message of what we just discussed. Okay, so from purely energetic arguments, it's obvious that the input of energy I'm supplying must balance the dissipation statistically. Right? Or that means in a given experiment, if you take a large enough time window, you'll find that a time and space integrated input of energy balances the dissipation. Okay, because these changes are going to be small. And typically, what will happen is, if the flow is turbulent enough, that means RE is large enough, you'll be inputting energy at the large scales. Right? And all the dissipation is going to happen at small scales because, of course, the viscosity can only act at a small scale. Another way to say that is, if I rescale my Reynolds number with some small scale, it will become 1. Right? Because RE is Lu by nu. If I take small l, small u by nu, that will be 1 at that small scale. That's why viscosity can become important again. Okay, so you must have small enough scales in the flow so that this term becomes important when I rescale with the small scale length and small scale velocity. It's like redefining the Reynolds number. Right? So at large scales, this term will really be 0. That means if I somehow filter the velocity and only look at the large scale smooth motion, there this term will be very small. But now if I look at the higher and higher spatial fluctuations and use those smaller scales, this will become bigger. Eventually it will become order 1. Okay, that's the idea. Okay, so this is the basic intuition that lies behind what's called Richardson or Kolmogorov cascade. Okay, so the idea was, which Richardson realized, Kolmogorov also had it independently, is just this, that I would be feeding energy at the large scales, it can only dissipate in the small scale. So spontaneously the fluid must set up a whole range of scales from the large to the small. Okay, and beyond that, the energy that I'm supplying at the large scale must make its way to the small scale to be dissipated. And that's what requires these scales with their energies. So just using the simple idea, what Kolmogorov worked out, so Richardson had this qualitative picture of a range of scales, okay, or a cascade of energy. But what Kolmogorov worked out is how each of these scales, how the velocity would depend on the length, okay, across all these scales such that this thing can work out. So that's what we're going to do next. Okay, so the reason what I'm going to show you now is called a phenomenology is because it's not derived rigorously from the Navier-Stokes. Okay, as you will see, it's based on, if you like, scaling arguments of energy budget and so on, or you can also get these results just from dimensional analysis. Right? So if they're not rigorous, you kind of hypothesize them based on scaling arguments, and when we look at experimental data, it seems to work out. Okay. And that's pretty much the best we have right now in turbulence. Okay, so fine, let's start with the basic idea, right? So Richardson said, okay, I have these, I'm going to force the fluid at some large scale, right? Capital L, right, with some velocity, capital U. So my forcing F will impose onto the fluid the large scale L, and which are rotating at some velocity, capital U, right? This is just a cartoon, but you can imagine this. These are the large scales, right? So energy is being input into the large scales. And now somehow I have to generate right? Some tiny small scales. Okay, these small scales have some small scale size, which you call eta. Okay, eta. So eta is, instead of capital L, I'm using eta. Okay, and they are spinning with some velocity u eta. Okay, and this is called the Kolmogorov length. Right, this is where the dissipation will start. This is the Kolmogorov length scale. So you start at the large scale and input the energy, right? And the length scale at which viscous dissipation starts, then of course if I go below it will dissipate more and more, right? So that threshold, if you like, where dissipation can actually happen is called the Kolmogorov length scale. And so if I input a certain energy, which I'm going to call epsilon, right? So it's energy per unit mass per unit time if I put into the fluid. At stationarity, the dissipation would also be the same. Because remember, that's what we derived earlier, right? Input of energy is equal to dissipation at stationarity. So if I call the energy input per unit mass per unit time epsilon, right, that's what's entering the fluid. Same thing is getting dissipated at stationarity. Okay? So the dissipation, energy input is happening directly, F dot U, right? And dissipation is happening through the viscosity nu grad U double dot grad U, right? That term is dissipating stuff, but at this small scale. And now the important point of Richardson was that, okay, it has to somehow make its way from these big scales to the small scales. So he postulated that there is a cascade of energy because you are putting in energy here and you're taking it out at small scales. So in scale space, if you like, not physical space now, across range of scales, if you like, you can think of it in terms of Fourier modes of different wave number k, right? I'm inputting at low wave numbers, I'm dissipating at large wave numbers. So in this scale space, I have to have a flux of energy, cascade of energy. So there must be big eddies somehow transferring energy to smaller eddies, somehow transferring energy to smaller eddies, right? And so on. And so this is where there will be an energy cascade. Okay? In scale space, from large scales to small scales, right? So you can see this in a periodic box. You can do this thing across Fourier wave number space. You can actually derive relation for this cascade. Okay? But if it's non-periodic, then you will have to use some other ways of specifying some coordinates at different scales. But the basic idea is that you can think of it, I have some big vortex, right? And that big vortex breaks down, makes smaller vortices, they break down, make smaller vortices, right? And eventually you reach a small enough length scale, right, where you can directly dissipate energy into heat. Right? And the important idea is viscosity only acts here. That means if I were to look at the dissipation term and rescale it with the appropriate length, the Reynolds number, here Reynolds number is too large. That just tells me viscosity is not important. As I change the length, the Reynolds number becomes larger. Eventually it becomes order 1 at the Kolmogorov length scale. And that means now viscosity is important. The dissipation term can convert the input energy into heat. So across these, I'm going to generally call the length scale L, right? The velocity scale UL. Okay, and then there will be a turnover time. So if you can imagine, again, these are just cartoons, right? You think of a small eddy, right? And this eddy is rotating with some velocity UL, it has length small l. Then the time scale tau L, right? The turnover time, just dimensionally, is going to be L by UL. Right? And I can have the same relations at the large time, at the small time. Okay, now what I want to do is, with this picture in mind, what Kolmogorov did is to say, okay, if this is true, then all I am controlling is the energy input, right? And then where this dissipation happens depends on the kinematic viscosity of the fluid. Right? So just from these two numbers, I should be able to tell you how the velocity at any scale is going to behave, right? And also how much smaller is this Kolmogorov scale compared to my large scale, right? That's sort of obvious, because if the viscosity is large enough, this eta will become same as capital L. I'll have a nice laminar flow. It's only as the kinematic viscosity is made smaller and smaller, this scale separation starts. Right? So the objective now is that given epsilon and the kinematic viscosity nu, right, I want to find a relation for eta, okay, the length scale at which dissipation starts, and how UL behaves as a function of L, etc. Right, so remember I said if this velocity scale is proportional to L, I will not be able to dissipate energy, right? Because the gradient will stay the same. So UL must change in L in some way that is weaker than L. So how exactly should that, what should that be? Can I obtain all of that information just by specifying epsilon and nu and using this idea, right, that the epsilon I put must somehow get dissipated. Okay, so for this I know now that input of energy is equal to epsilon. Now to follow through the cascade, I need to figure out an expression for how the energy is transferred from this one scale to the next. Right? So eventually dissipation, I have a formula. It is involving the viscosity, right? It is the viscosity times the gradient square. But before we come there, is there an expression for how the energy is transferred in this intermediate regime? Right? That's what I need. That is a missing link. Right? So what Kolmogorov hypothesized is that right, the energy transfer across the intermediate scales right, he said that the energy transfer that happens across these intermediate scales is independent of the viscosity because they are still much, much larger than whatever scale the viscosity first becomes important. Okay, so he calls these the inertial range. That means only inertia is important, no viscosity. And so if it is independent of nu, it must only depend on UL and L. And nothing else is there, right? So if I have a certain scale, all I know is it has a certain length of the eddy, certain velocity scale of that eddy. And I'm saying that eddy is going to transfer energy to a smaller scale. The rate of transfer cannot depend on viscosity because viscosity has no role to play at these larger scales. It's only playing a role when I reach this Kolmogorov length. So if this is true, that viscosity doesn't affect the transfer of energy across these intermediate scales, then energy transfer rate has to only depend on this. Okay. And either by using scaling or just by dimension analysis, you will see that, right? Therefore, the energy flux, okay, must just be U cube by L. Right? That's obvious, right? Because you have energy per unit time, no? So the kinetic energy is UL square, and that time has to be related to the dynamics of that eddy, right? So the typical time scale of that eddy, as we said, is L by UL, right? That is this tau L. So what you're saying is, I don't know exactly how it's going to happen. Some fluid mechanical instability will take place, okay? But as long as I'm saying that there is such eddies which are characterized by L and UL, and therefore time scale L by UL, whatever the flux is happening, the kinetic energy of that scale, which is UL square, must break down and transfer on time scales of its own dynamics. So it's saying that the energy flux is independent of nu, and I should say and of the large scale forcing. Right, those two things. So the viscosity is too small to affect what's happening here. At the same time, these scales are much smaller than whatever mechanism I'm putting in energy. Let's say I have a big fan. Right? The fan will definitely affect how energy is being transferred at its scale. The shape of the fan, how I'm stirring it. But once, let's say, you go 10 times smaller than the fan blade, right, then this seems reasonable that whatever is happening on those small eddies should not be dependent on what's happening with the fan, right, as long as energy input is same. So if it doesn't depend, the only thing I'm controlling is the fan and the viscosity. If both these things cannot influence it, it must be doing something local, right? And the only local properties are its own velocity and length. So the only quantity you have is this, right? And the actual physics of how it happens, that is part of turbulence research. That is a fluid mechanical question, right? So what exact instability happens to disrupt the vortex, to break it down, that's a different question. But just from dimension analysis, you can say, okay, that this must be the flux. So we know that this UQ by L at these intermediate inertial range scales will control the flux from one scale to the next. So I know input is epsilon, I know ng flux is this, and what about dissipation? This is dissipation which starts at scale eta, right? Viscous dissipation. This must, of course, we know the formula, right? It's nu gradient square, right? Grad u double dot grad u. So it just be u eta square by eta square. Right, so the gradient of velocity is the velocity at the scale divided by the length, right? So that is the dissipation. Right? Or if you want to write it more generally, right? Let me say it, then we can do it the other way, right? So when dissipation is active, right, at small scales, right, this will be true. So if I continue to say L is the scale, when L is intermediate scales, I'll have this relationship. Right? But when I reach sufficiently small scales, then I know that the dissipation will be related to it in this way. And now, of course, I must use the fact that the input of energy must be equal to the dissipation, right? So this must be equal to epsilon. The input and the dissipation are same. Right? But if what I'm sending in is coming out at the bottom, that must also be what is cascading through, right? Otherwise, I will have some accumulation. So this is also epsilon. Okay, so you see I have two relations now, relating the velocity to the scale of the corresponding eddy. Right? One is in the so-called inertial range, where viscosity does not operate, where the energy is simply cascading through inertial effects. And the other is inside the dissipation range, right, where dissipation is the dominant thing and viscosity plays a role. Right? So you can see already that I'm going to have two different kinds of velocity scalings. Right? So this is inertial range, right, where viscosity doesn't play a role. This is the dissipation range. Right? And they have two different implications for the velocity. Right? So here I have the velocity will vary like epsilon L to the 1 by 3. Just to emphasize it, let me write it as okay, so that comes directly from this, right? And in the dissipation range, I have Just rearranging this. And now you can already see some very different behavior, right? So this is called rough. And this is a smooth field. Right, so what this tells me is when I'm in this inertial range, right, the velocity scaling is actually much larger than I would expect if I had a smooth, what we would call laminar field. Right? So when I say I have a laminar field, the flow field looks nicely ordered. Mathematically, it just means that I have smooth gradients. Even if the gradient is varying, it's varying smoothly or almost constant. Right? So when the gradient is almost constant, the velocity must be proportional to L. This is what will happen in any laminar flow. And so it's smooth mathematically in the sense that its derivative will exist. Right? So if you have such a velocity field, at any point its derivative will be bounded and it will be related to epsilon by nu to the half. Right? That's what happens that's why we call it smooth. Right? So its derivative is some nice bounded function. This is the magnitude of the derivative. Okay, so it will be strong certainly as nu goes down, but you're not going to blow up or something. Right? But if you look here, you will see the derivative is not defined. Right? Because if I take u by L and take L going to 0, what will happen? U by L will become L to the minus 2 by 3. As L goes to 0, to blow up. So a way of thinking about this is if you take the full velocity field, which has all scale information, and I do some kind of filter. Right? You can do Fourier filter, wavelet filter, whatever your favorite filter is, but you apply some filter so that you say, okay, my full velocity field is a sum of different fields. I have a sum of only the smoothed large scales. Then I have finer features, then I put finer features, like how you would do it in image processing. You can take an image and you can filter it out, right? Or you can do this kind of moving average, some way of decomposing an image, if you like, into the smooth variations and then the smaller and smaller fluctuations. So you can do this mathematical operation on a velocity field. And that's one way to think about these scales. Right? So the very smooth behavior is on top. Viscosity cannot play a role. The very rough behavior is here, right? The small scales. So what you see is those different fields will show different behaviors with their length. Right? Here in this intermediate regime, it will look very rough. That means if you look at something, some property of the field, maybe just the magnitude of u, right? It will have sudden jumps, very rapid fluctuations. Right? It will really look turbulent. And if you zoom in, at some point you will start looking very smooth, like as if you're laminar. Right? That's just saying that if I take a microscope or if I become small and jump into a turbulent flow and become smaller than the dissipation range, I will think I'm in a laminar world. I will not even know that I'm turbulent. Of course, my environment will change in time. But if I look at how things are varying in space, it will look like I'm in some time-dependent laminar flow. I'll only see the turbulence when in this intermediate range, because now I'll see the velocity is changing very rough. You can think of in your mind some kind of rough sea, right, where there are sharp waves. So this is the velocity field is changing rapidly. So that statistically, if you look at typical velocities over length L, they will not scale like L. They'll be much larger, right? So there are ideas to think of L being small. So if L is small, L to the 1 by 3 is much larger than L. Of course, small relative to capital L. Right, so remember, I scale the Reynolds number with capital L. So relative to the capital L, this is small. Okay, so L to the 1 by 3 is bigger than L when L is small. Right? Don't think of it the other way. We think L square is bigger than L. That's because I'm thinking of large L. But here I'm starting with the scale, Reynolds number, everything was scaled with a big scale. I'm now shrinking. So as I shrink, I'm not decreasing my velocity fast enough to remain smooth, right? I'm actually going to have much, much larger velocities than being proportional to the distance. That's what I meant by energetic scales. So it is this behavior that allows you to dissipate. Right? So somehow turbulence produces this behavior so that you have small scales but which are spinning much faster than they would in a laminar situation, right? And so you dissipate. It's only when you are fully dissipating that you again recover this smooth behavior. Okay, so that's fine. What we have done is just using this idea, we have come up with these scalings for how the velocity field will behave across different scales. What we have left to do is find out when will this happen, right? At what point will we hit dissipation and change the behavior to this kind of locally laminar flow? So I want to find this eta. And the idea I'm going to use here is to say, okay, I know that this difference is there in my mind, but at some place they have to meet, right? So the input of energy has to meet the cascade at the top of the cascade, top of the inertial range. That's what I used here effectively. So basically at the large scale, it also has to dissipate and it has to transfer. So epsilon will also be capital U cube by L. But I can use the same idea at the bottom, right? So at the start, at this Kolmogorov length, it's at the end of the inertial range, at the beginning of the dissipation range. That means I can find eta by saying eta must satisfy both these relations, okay, because it's at the boundary. Okay, so by definition, right, is at the boundary, right, of the inertial range and the dissipation range. So I should require both relations to be satisfied, right? That means I have u eta cube by eta to be equal to epsilon, right? And that must also be equal to nu u eta square by eta square. So I have two relations. I should be able to solve for eta in terms of nu and epsilon by eliminating u eta. So can you do that and tell me what you get? So basically I want to find eta in terms of the known things, nu and epsilon, right? So you keep one relation, use the other relation to replace u eta into this guy, right? And then you can tell me what eta is. So that will be a prediction, right? We'll be able to tell, okay, given an epsilon, that is the amount of energy I'm pumping into the system, and the fluid viscosity, I can tell you how small the Kolmogorov length is relative to the large length scale, capital L. So on top, I should also write that the input is equal to the cascade, of course, right, at the top. So then I will have epsilon is also capital U cube by L. Right? So epsilon will specify this, right? If I know the large length scale L, then I can get U, capital U. And now I can find, relative to this large length scale, what is the Kolmogorov length, how much smaller is it going to be? Right? Right. So you get eta is nu to the power 3 by 4 epsilon to the minus 1 by 4. Okay. And then one can also show, right, I'll just show you to save some time, that if you want to know, okay, that this is the length scale, right, then I can immediately calculate the velocity scale, right? Remember, the velocity scale also satisfies this relation, right? So it must be just right, and then eta I can put in from here, so I can get the typical velocity magnitude of the small eddies. I can also get the time scale, right, as eta by u eta, right? Which if I substitute everything, for example, you will get eta to the so you can write it eventually in terms of nu and epsilon. That's what I'm trying to say. So yeah, so once you have this, you can use these relations also to find the typical small scale velocity, the typical small scale turnover time. Okay, so these are useful things. We'll also be using them because this allows me to estimate, if I start with some large scale, certain energy input for a given fluid, at what scale will the flow become smooth? Right? When will dissipation first be important? This is obvious. The one obvious importance is if I'm going to do a simulation of a turbulent flow. Right? So I'm going to solve my Navier-Stokes equations in a box at some macroscopic Reynolds number with some input energy rate. Right? I want to be able to simulate this. If I want to simulate it properly, the smallest grid scale must be smaller than the Kolmogorov scale, because only then I will have a smooth flow. So if I stop my grid when the grid size is bigger than eta, no chance I will, first of all, the simulation may just blow up. Right? Or it may give me some result that is stable only because of some huge numerical diffusion or numerical viscosity. Right? So to get an accurate result, I need my smallest grid length to be much smaller than eta. Because then at the grid scale, I have some smooth flow, which can be well resolved by those corresponding grids. Right? So this is the basic requirement for what's called a direct numerical simulation. It just means solve the Navier-Stokes with enough resolution. And enough means smaller than eta. Okay, the important thing is, as the RE increases, eta will get smaller and smaller, right? Because as you decrease nu, eta will decrease. Not only eta, the time scale also is going to decrease along with eta. That means I not only have to take smaller grids in 3 dimensions if I'm doing a 3D flow, right? So it's not just decreasing grid in 1D, I'm decreasing grids in 3D. So that will blow up my memory and whatever. And in time, when I'm time marching, if I'm evolving the simulation in time, I need to make sure I capture the smaller scales, otherwise the whole flow will not work well. Right? I won't be able to dissipate properly. So the delta t at which I update my numerical solver also has to be smaller than tau eta. So this is why turbulent simulations are extremely costly. Because if you like, as I increase RE, I am increasing the cost in 4 dimensions, 3 spatial dimensions and time. So DNS is very, very difficult, right? We are very quickly, even with the biggest computers, we cannot do very large simulations. So typically, if you take, let's say the standard computing cluster we have in IIT Bombay, you can do maybe the simulation of 1 meter cube in a week's time of constant computing, right, over a large number of nodes. So if you take 1,000 processors for a week, maybe you can do this 1 meter cube, right, with the latest computers. So and imagine this is like a very small thing, right? You want to do like serious industrial flows, atmospheric flows for weather, climate prediction. So it's completely still now well beyond trying to do any DNS. This is why you need this kind of phenomenological theories. This is why you need stochastic modeling. Right? Because if I want to figure out how some gas pollutant emission is being spread and influenced by turbulent mixing, right? Because turbulent mixing in the atmosphere will spread the pollutant. I cannot sit and do a DNS, it's impossible. So I need to have some kind of way of modeling this. Right? This is why these stochastic models are still relevant. Right? You cannot just replace it by doing direct DNS. Okay. So anyway, so that is one immediate implication why we would want to calculate this thing. Right? Apart from the fact that in my stochastic model, if I'm going to build a velocity field, my velocity field to be reasonable has to have the character I just said, right? I should have a range of Fourier modes which satisfy the magnitude going like L to the 1 by 3, where L is the inverse of the Fourier wave number. Okay, so I can construct a sum of Fourier modes so that the amplitudes behave in the correct way. Right? Then I would be able to mimic the spatial structure at least of a turbulent flow. So all of that I can know just from this Kolmogorov phenomenology. No need to solve the Navier-Stokes. That's why I'm talking about this in this lecture. Okay, so we have derived now the Kolmogorov length, right? How it depends on the dissipation. Okay, and a nice thing to try now. Okay, so what I'm saying here is, let me plot it, right? So if I look at the typical velocity scale, L, versus the length scale, right? Or let me do, length scale. Let me plot it versus 1 by L. Okay, so as I go to smaller and smaller length scales, right, this is increasing. So these are small scales. So here there will be capital U, right? I will then hit some rough behavior where I go L to the 1 by 3, right? And then at some point it will decrease faster, right? It will go proportionally to L. And this is 1 by eta. This is the Kolmogorov length. Okay, this is 1 by eta. Right? So you have this picture of a rough field then a smooth field. This is the inertial range, that's the dissipation range. Okay, of course this line is not L to the 1 by 3, right? It's L to the minus 1 by 3, but I'm just, because I plotted as 1 by L. Right? But this behavior as U eta goes like L to the 1 by 3. And that's what I'm trying to say. Okay, now it should be interesting exercise to check what is the Reynolds number at the Kolmogorov length scale. Right? Because the whole point is that Re at the large scale, right, is much, much less than 1. This I know. Okay, and Re even at the length L in general in the inertial range, right, that's one way of saying. So if I rescale Re with capital L, capital U by nu, that should be very small. That's the basis for this whole argument, right? That dissipation cannot operate at the large scales. Similarly, in the inertial range L, right, where Re is L UL by nu, where L and UL satisfy this relationship, even there the Re will be small. And then it first starts to be important, means Re should become order 1 when I use eta. So I can of course check these things, but for simplicity, let's just check this, then automatically it will be clear the other relations will follow. And Re has to be greater than 1, means Re is, sorry, other way around. Sorry. Right? Re is big, so dissipation is not important. Re will become smaller than 1 if I go sub-Kolmogorov, if what I have done is correct. So let us just see what is Re at Kolmogorov, then automatically the other relations will have to hold, right? So let's calculate Re at eta. Right? What is this going to be? U eta by nu. Can you check and tell me what it is? Using the relations you have now, right? Right, so I am saying calculate Re at the Kolmogorov length, right, to see whether it is in fact order 1. So U eta by nu, not U eta. Right? So U eta is just epsilon to the 1 by 3, eta to the 1 by 3 into eta. Right, so that's eta into to the 4 by 3. Right, now we substitute eta here. Right, you will immediately see that you should get 1. Correct, because you have epsilon. So eta to the 4 by 3, 4 by 3, 3 by 4 will become nu. That will cancel out to the bottom nu. Epsilon to the minus 4 into 4 by 3 will be minus 1 by 3. That will cancel out with the plus 1 by 3. You will get 1. Okay. So it's worked out. I mean, that's the relationships we use, right? So remember in the dissipation relation we derived, right? You had input of energy is equal to 1 by Re times U square by L square, basically. Right? So for those things to balance, what is the length scale? That means Re should be 1. Right? That's what we used indirectly, therefore it should work out. Right? So indeed the rescale Reynolds number, right, at the Kolmogorov length is 1. That is where the dissipation first starts. So now you can see if instead of eta I had used the dissipation range behavior of UL, I would get Re smaller than 1. If I use the inertial range scaling for the velocity and L, I will get Re greater than 1. Okay, and so this is really the boundary point. So one way to think about the Kolmogorov length is that small length scale where the effective Reynolds number is 1, and therefore dissipation can come in. Right? Above that length, the Reynolds number is much greater than 1. Viscosity has no role to play. Okay. And how we can, and the whole point of Richardson is that somehow the fluid generates all these scales by cascading energy through scale space until it hits the Kolmogorov scale, where then below that it can dissipate to heat. And that's how the energy balance is maintained. Okay, so all of this we have derived just from the energy balance, and so that's the first idea, that there must be input of energy at large scales must be dissipated at small scales as the Reynolds number, nominal Reynolds number increases. Right? Large scale Reynolds number increases. That's the first idea. The large scale energy input, small scale dissipation. The second idea is that therefore range of scales must be set up through a cascade. Okay? And importantly, the transfer of energy across scales in the intermediate range is influenced neither by viscosity, because those scales are too big, right? Their effective Reynolds number is still greater than 1, nor by the large scale forcing, because compared to the large scale forcing, these intermediate scales are still much smaller. Right? So that is of course a complete hypothesis. Right? We have no mechanistic way of showing it from Navier-Stokes, but it's a reasonable assumption to say that if I'm having a big fan the size of this room, it will not affect motion at this small scale, right? Because all kinds of fluid mechanical processes are intervening. Somehow this scale has forgotten its large scale forcing. So whatever is happening here is independent of that. At the same time, this is too big compared to the Kolmogorov length, which is very small. So the viscosity cannot influence motion at this scale. So therefore, that whatever is happening fluid mechanically, right, has to transfer energy at a rate that is given by the velocity at this scale and the length at this scale. So that's how you get the inertial range scaling, right? That UL cube by L is equal to epsilon. That is the main idea, right? Then the rest is usual energy balance, right? When we go to the dissipation range, we know that dissipation is nu times grad u square, the grad u double dot grad. So if you like, the main idea is just, the main hypothesis is this, right? That apart from energy balance arguments and usual expression for dissipation, those are normal fluid mechanical things. The main new idea, realization, is that intermediate range of scales are not affected by the large scale forcing, nor by the small scale dissipation viscosity. They are doing their own thing and just cascading the energy. Okay, and that, with that you can derive all this stuff. Okay, so there are a couple of more things I wanted to say, which I think I'll take up in the next class. So we have now more or less derived this phenomenology, right? What we need to do is obtain from this behavior the energy spectra, right? Because that is what people typically calculate and which can be verified with experiments. Also, that is the information we would need to cook up some synthetic velocity field. Okay? And then we can also look at some other things from this phenomenology, like what are the temporal fluctuations in turbulence, because in the end, if you want to replace it with a delta correlated flow, we should be aware of the approximation we're making. So in other words, in the next class, we'll look at this Kolmogorov phenomenology in terms of its implications for our stochastic modeling. Okay? And then we will proceed with the applications. Okay? Thank you.